Hey everyone, today I'm gonna talk about Yukawa couplings, how they look like at infinite distance. And then on the second part of the talk, I'm gonna connect all these ideas with phenomenology, with the neutrino setting in the standard model. So this is based on these two works from last year with Fernando Marchesano and Luis Ibáñez, and some work in progress we are doing right now. So let's start. Okay. So we would like to explore infinite distant limits, and infinite distant limits is something that has been explored in the context of the Swampland program. That's because you find patterns, you find some properties of quantum gravity. So for instance, you all know that if I want to send some gauge coupling to zero, we probably are at the infinite distant limits in order to send this gauge coupling to zero, because we find some global symmetry, which is something that we don't like in quantum gravity. We find some tower of states that is telling me that my effective field theory is breaking down. And and even a more consistent things, it depends on the different limits and the different scenarios. But I am interested in doing this exploring of the infinite distant limits in supersymmetric chiral theories, because they are a bit more relatively unexplored, but they are very important for phenomenology. Because one of the questions that we had at the beginning is that what happens, we understand what happens with gauge coupling, more or less, but what happens with the Yukawa couplings? So can I think in the same way that if I send some Yukawa to zero, it's because we are at an infinite distant limit? A priori, there's no obvious reason why this is something bad for my effective field theory, but I will try to argue in this talk that indeed it is. This is important for phenomenology, as I just said, because for instance, if I consider my standard model, and if I consider my moduli space of the standard model, so I parameterize here, this is my moduli space and each point is the parameterization of the masses of the different fermions in the standard model. My intuition says, and the intuition can say that the order 1 Yukawas are in the bulk. And whenever I move to the different corners of my moduli space, then I can reach some region in which all the masses of the fermions are zero, almost zero, or I have some hierarchy in the different Yukawas, like in the standard model. If this intuition is right, then for the standard model, we have predictions. Because if we consider that neutrinos are Dirac in the standard model, the Yukawa coupling is extremely small. That meaning that we would be in one of these corners in the moduli space, and then probably there are gonna some swampy restrictions that are gonna appear. Like for instance, maybe there is some global symmetry that arises, or there are some large extra dimensions that appear, and this is what we will see in this talk. Okay, so in order to test this idea, we go to intersecting branes in type 2A. We compactify type 2A in a Calabi. We break supersymmetry from n equals 2 to n equals 1. And in order to have a gauge theory in 4 dimensions, we need to introduce D6 branes here. The different configuration of the D6 branes is going to give me the different symmetries in the 4D. And we know that the different spectra of particles and the different under which they transform under different symmetries that these branes has, we need to quantize the open string. The open string quantization give us some massless chiral multiplet. So in this chiral multiplet, you have like your favorite fermion in the standard model. And when you quantize the string, you realize that there are some oscillators, different oscillators, that gives you some massive chiral fields. And they were called gonions in this paper. These are some tower of states that appears in the intersections between the different branes. And the mass is proportional to the different angles. Something that is going to be very important for this talk is that whenever two branes, the angle goes to zero between two branes, there's going to appear a tower of states, which are the gonions in this case. Okay, so I am interested in Yukawa couplings. Yukawa couplings in this context appear in the intersection of 3 branes. So they have to form a triangle. And in the different corners of the triangle, I have the different fields that appear in my Yukawa. So I have my Higgs field, my right fermion, and some doublet here, for instance. And the Yukawa in this context appear because there are some worldsheet disk instantons that connects the different disk branes. This was computed in these papers from the two perspectives, from the type 2A perspective and from the type 2B perspective. And essentially what this long formula tells you is that the Yukawas depends on for the dilaton, the volume, and a very ugly structure with gamma functions that depends on the angles between the different branes. So these are the angles in this triangle here. And this is going to be the important part of the talk. They also depend, of course, in the superpotential, which is holomorphic in the in the Caleb moduli. Okay, so with this local geometry, we know that the Yukawa depends on local geometry, and we can also extract some more information out of the Yukawa coupling. We can extract, for instance, the kinetic terms of the different fields that arise in the Yukawa coupling. With this 14 equal to 1 formula for the Yukawa, we can see that the kinetic terms of the Higgs, the right fermion, and the doublet is given by this structure. And with this formula and this one, we can see how the calorimetric or the kinetic term looks like. Before going to take some infinite distant limits in this context, let me do some type 2B detour. So everything that I'm going to say in this talk can be mapped to type 2B. And it's very important to have this map into account for computing things with Yukawas, because essentially in type 2A, the Yukawas are they have a stringy origin, but in type 2B is pure classical dimensional reduction. So when you have ND6 branes in type 2A, you have a U1 gauge theory. And if now you do 3 T dualities in 3 different radii, you find that you are with D9 branes and 0 flux. But I am interested in having some intersections. So what one should do is to give some bev to some of the scalars that parameterize the relative position between the different branes. And this is going to break the symmetry from the UN to the different smaller groups. But this T-duality, the T-duality of this scalar, is essentially the Wilson line in type 2B. And this is a linear, it's a Wilson line with that depends linearly in the position. And so we have some background fluxes in the different two cycles. So you have now magnetized branes in the duality map, and magnetized branes with some background fluxes breaks symmetries from the UN to the different smaller groups. It depends on the configuration, of course. And the last thing is that for the Yukawa couplings, in type 2A, they arise, as I just said, with these instantons contributions. And the gonions arise because they will have open strings at the intersections. This is something that I already showed you. But from the type 2B perspective, the Yukawa couplings are simply some integrals over the internal dimensions of the dBi action of the D9 branes. And the gonions are simply solution of the Laplacian when we have a non-trivial flux here. So they are called in the literature usually Landau levels. Okay, so let's take some limits for the calorimetrics. Remember, these are the kinetic terms of the fields that enters in the Yukawa. And I consider some intersection between two branes, and the fields arise at the intersection. And I would like to take some limit in which all these angles are small. When these angles are small, these gamma functions can be approximated by this expression. And the next thing one can do is one can take a limit in which this θ2 goes to 0 and θ1 and θ3 goes to the same order. This is because I want to respect the supersymmetry condition, which is here, between the different branes. If I take this limit, what happens is that the kinetic terms blows up, as you can see here, but we have some tower of gonions. This is interesting because, as I said before, whenever one of the angles goes to 0, there are some tower of states, which are the gonions that appear and are coming down. One of the things that you can also do is to express the kinetic terms in terms of the masses of the gonions. And you can see that this expression, one of the interesting things is that it can be motivated from the emergence proposal. This emergence proposal is the idea that all the terms that appear in the IR arise when you integrate out different towers from the UV. And if you do this kind of calculations with gonions, this kinetic term appears. And can only be done with gonions because they have the right charges under the symmetries that the D brane have. Okay. So now let's take an infinite distant limit, but for the Yukawas. As I said before, the Yukawas depends on the volume, the holomorphic superpotential, and this depends on Kähler moduli essentially. But this red term here depends on the complex structure. So one of the goals is to have this theta term very suppressed, so that in order to get that, I need, as before, to have one of the angles very small. So I take a limit, as before, that one of the radius goes to infinity, R1, the theta 2, I'm gonna take. R1 goes to infinity, and R2 goes to 0. If that happens, then I have this kind of shape for the for the torus, and the angle goes to 0 at the infinite distance. 1 second. Okay, so according to the Swampland distance conjecture, whenever I have a tower of states becoming massless, whenever I take an infinite distant limit, I have a tower of states becoming massless, and indeed we find those. We find some gonion tower because the angle goes to 0 here, and we find some KK towers and some winding tower because here I'm taking a decompactification limit, and here I'm shrinking one of the circles, so I have a winding tower. One of the things that also we find is that we recover a global symmetry and at this infinite distant limit, because the gauge coupling of the gauge theory that is living in the brane goes with the 1 over the volume of the 3 cycle that is wrapping. And since this 3 cycle is very large, the gauge coupling goes to 0. But most importantly, and one of the results of the paper, is that the Yukawa coupling can be expressed in terms of the tower of the gonions that appear in the different intersections. So I am missing here some third brane. So these are 2, and for the Yukawa, remember that I need a triangle. But I am just focusing on one of the corners. So one of the results is that the Yukawa goes to 0 whenever one of the towers in one of the corners appear, essentially. And when this goes to 0, as it happens here, the Yukawa goes to 0. So this is a bit decausistic. This is a very silly model, but it can be done in more difficult or more involved configurations. But we believe this is a general result, in the sense that we are using angles, we are using tower of states that are charged under the different symmetries, and this can be generalized in different in general Calabi-Yaus, because essentially it's a local. These are local parameters or local variables in your manifold. Okay, so let me summarize a bit the first part of the talk. What we have done is that we have seen that whenever I take some Yukawa coupling to 0, there is some gauge coupling that also goes to 0. So I recover a global symmetry. So that means that indeed having a very small Yukawa couplings is a bit problematic at the infinite distant limit. We are at the boundary of the modular space. We also find that there are some tower of states coming down. We have gonions, and we have some KK modes and winding modes. And because of that, we have some dimensions that open up in pairs. Because as I showed you in the example before, there are some radius that goes to infinity and some other that goes to 0. And in this model, in these scenarios, you can compute the species scale. The species scale, of course, depends on the limit, as you all know. And there are essentially 2 limits in this context. You have an emergent string limit, where a D4 is wrapping a 3 cycle, and the tension goes to 0, so it's an emergent string limit. Or you have a decompactification limit, in which the KK modes, the winding modes, and the gonions are the leading tower. If you compute the species scale with these towers, you find that the species scale is the string scale, but it also coincides with the 6-dimensional Planck mass because you are decompactifying in 2 dimensions, and that is the fundamental scale in 2 dimensions higher. Okay, so let's go to the second part of the talk. The idea is that I'm gonna review, I'm gonna apply all what we have learned to the neutrinos in the standard model and in string theory. But first, let me summarize a bit what are the different neutrinos in the standard model and how they are implemented in string theory. So for Majorana neutrinos, it's very difficult in the different models that have been discussed in the literature. It's very difficult or impossible to generate perturbative terms that contains Majorana mass. So what people do is to introduce non-perturbative effects. What usually people do is to wrap a D2 brane, wrap in a 3-cycle, that intersect different D6 branes. This is gonna give some non-perturbative terms like this one, which is the Majorana mass. And one of the things now that you should take into account is that in order for the seesaw mechanism to work, this Majorana mass has to be large enough. To do that, this volume has to be small in general, and that is one of the challenges. The second challenge is that the toroidal model is non-realizable. You cannot do this because of the different symmetries that you need in order to generate this kind of terms. And in general, it can be possible, but it's something that is difficult in principle. For the Dirac neutrinos, things are a bit more easy, as I discussed in the last 15, 16 minutes. And small masses of the neutrino or other particles arise at large distances in moduli space. We have also in these limits well control of the string coupling. And also even in simple toroidal models, things are easy in order to see how the caustistics and how these patterns arise at the infinite distance. And the last point is that Swampland criteria prefer Dirac neutrinos. That is because there are some works that argue that if you compactify the standard model in a circle, you get anti-de Sitter, non-supersymmetric anti-de Sitter. And there is some conjecture, the anti-de Sitter, non-supersymmetric anti-de Sitter instability, that tells you that that should be unstable. In order not to wash away the instability, then you need to consider Dirac neutrinos, and that cannot go away if you consider Majorana ones. That is a bit the idea. Okay, so with this in mind, let's go to the setup that we considered in the paper. The idea is that we have that type 2A with different branes, 5 branes, and the black branes is giving me the standard model symmetries, or almost, because we have here a stack of 3 branes, which is giving me the SU3 times this U1. Here I have 2 branes, which is giving me this SU2 times this U1. And then I have this extra 3 U1s, which is this one, the C tilde, and the D, these 3. Okay, when you have these configurations for the standard model plus extra U1s, what you should take into account is that what are the linear combination of U1s, which are anomalous or not, or which are massless or massive. You can check in this example that we discussed that this particular combination of U1s is massless and non-anomalous. So we call it the hypercharge. And with this, I complete the standard model. One can also check that the rest of the linear combinations are massive or anomalous, which become the massive, because one of the things that happens is that whenever you have an anomalous combination of U1s, there is a Green-Schwarz mechanism and a BF coupling such that this gauge field get a mass. Okay, so moreover, one of the important things of this model is that this blue stack or this blue intersection is hidden from the standard model sector. And that is essential in order for this to work. The idea is that in this C tilde D, you have the right neutrinos. and they are charged under this U1 symmetry with this gauge coupling, and I can tune the gauge coupling to the value I want. And if I do that, the good idea is that the good thing about this setup is that the hypercharge and the rest of the gauge coupling of the standard model are not affected. Okay, so I now, with this in mind, I want to compute the Yukawa coupling. The Yukawa coupling for the neutrinos are generated in this triangle here, as you can see, because you have the right fermion, the lepton, the doublet, and the Higgs. And what we have learned in the past 20 minutes is that whenever I have some angle that goes to zero, there is some Yukawa that goes to zero in that triangle. So I'm going to take that limit. I'm going to take a limit in which I grow a modulus in the complex structure as before, such that the angle goes to zero. If that happens, then I find a tower of gonions that goes to zero, because essentially the gonions depends on these angles. And the mass of the gonions is parameterized by the gauge coupling square in this model. Moreover, the gauge coupling goes to zero as before, because as I said, the gauge coupling goes with 1 over the volume of the 3 cycle, so also goes to zero. And most importantly, as before, there are a double decompactification, because we have some KKs from one of the radius and some winding from the other radius. So I have a decompactification of 2 dimensions, and they have this scaling with the gauge field, the gauge coupling. So the last thing one can compute is the cutoff of the theory. The cutoff of the theory, as before, is the string scale. We are in a decompactification limit, and it goes with the gauge coupling. And now the most important part comes here, because since the Yukawa coupling goes to zero in this limit, and if you check it in this configuration, it goes with the gauge coupling, now I can introduce the observational data, so the experimental bounds on the Yukawa coupling. This is the number of the experimental bounds that are in the literature. So now, since this gauge coupling is equal to this very small, ridiculously small number, I can back react everything to the different quantities that I showed you before. And with that, I can build this table. So essentially, for the sake of time, I'm going to discuss that the cutoff of the theory, if I do the numerics and I introduce the gauge coupling, is 700 TeV, which is not that high, the fundamental scale of the theory. We also find some gonion tower at 500 eV. And most importantly, maybe, is that we have some 2 large extra dimensions at 500 eV. So one of the lessons of this configuration is that whenever I want to make some Yukawa very small, I have to balance something. And here I have to balance the fundamental scale of my theory and the 2 large extra dimensions, the gonion tower, etc. Okay, I also comment here that if I try to do the same instead of with 2 extra dimensions with 4, the string scale is too low, is lower than TEF or the order of some TEFs. So let's say that the natural example is, or the natural limit in which you have realistic results is with 2 large extra dimensions. So now let me comment on some work in progress, and then I conclude. We are now working on Yukawa couplings in heterotic string theory. In heterotic string theory, things are a bit more difficult because essentially the Yukawas arise as in type 2B, doing some integrals over the internal dimensions. But here the Yukawas are parameterized by the Gokuv, Buffer, width, and superpotential, and the Kähler metrics. But the Kähler metrics here are computed via one harmonic forms that have valued in the vector bundle. And in general, it's very difficult to know these guys and to compute the Kähler metric. So there is a trick for this. The trick is to use the standard embedding. The standard embedding is the setup in which the vector bundle is equal to SU3, such that these guys here, the Kähler metrics, are equal to the metrics of the moduli space. So we now have more control because we know more a bit of these spaces, and we can have a hand to the Yukawa couplings. Also, one of the results in the standard embedding that people know is that the curvature goes with the Yukawa square. So here we have a rich arena, because if we understand the curvature of the complex of the moduli space, we know how the one of the Yukawa at least behaves. So for instance, at the conifold point, Yukawa couplings diverge because the curvature diverges. Also at K points, Yukawa coupling can go to 0. These are some singularities that arise in one parameter Calabi. It was studied in this paper, which is also interesting. And also in the large complex structural limits, the curvature can go to a constant value or can diverge. This is in relation, for instance, with this recent story, such that you have a divergence of the curvature whenever you reach a rigid theory in that limit. I now conclude, because I think I passed the time. Sorry for that. We have explored limits of Yukawa couplings in type 2 orientifold compactifications, and very small Yukawa couplings come at a price. So this is one of the lessons of this work, that I have a tower of conions, I have a tower of KKs, I have very small gauge coupling, and this is very powerful. This is a very swampy idea, but it's powerful even for the neutrino sector and for the standard model, because it links different physical quantities. So in the neutrino sector, I can link the mass of the neutrino with the radius of the extra dimensions, with the lightest tower of states that appear, with the quantum gravity cutoff, or even it can be linked with the cosmoical constant, with the electroweak scale, and even more things. So with this, I conclude, and thank you very much.